Today's video will demonstrate how to implement the stack. Hello, I'm James Helfrich. There are basically four implementation options if you want to create your own custom version of the standard template library stack. This video will demonstrate each of those four options. The first implementation option is the fixed array, and here we specify at compile time how many elements we could possibly have in our stack. The second is to use the list as the underlying data structure. This has the advantage of being able to accommodate any number of elements. The third is to use the vector. Like a list, it can also grow to accommodate any number of elements. And the final is to use a container adapter. We'll discuss each of these in turn. The simplest implementation is a fixed array where the maximum size is known at compile time. So we're going to start with our class diagram, and the stack is going to have our usual constructors, destructor, and assignment operator. It also needs to have a size and an empty. And for the fixed implementation, we need to have a member variable called number of elements, which is an integer. We're also going to be able to push an element onto the stack, and this takes a T, which means our stack needs to be a template class of type T. So what's the pseudocode of push? Well, we're going to say if num elements is less than n, then array square bracket num elements plus plus equals that new T. Well, I need a few things for that. First of all, I need to have a new template variable called n, which is the maximum size of my array. Second, I need to have a member variable called array, which is going to have n t's. And so what's the C++ declaration for that going to be? It's going to be t array of n as well as int num elements. And notice how I have two template variables. One is my data type, which is t, and a second with an integer, which is n, the number of elements. I'm also going to have a pop, and a pop is just going to say num elements minus minus. And then finally, I'm going to have a top, which will retrieve an element. And I'm only going to do so if there's elements in my collection. Now, this is my fixed array implementation. Now let's take a look at the list implementation. Here I'm going to have a single member variable called data. So I'm going to have the same class definition of stack of template T on how my constructor, destructor, assignment operator, size, and empty. And this is going to require me to have a member variable called data, which is of type std_list. So when I declare this in C++, I'm going to say class stack, and the member variable is std_list of T, which means, of course, I'm going to have an associated class called std_list, and the association be composition, and the numerosity be 1. I'm also going to have a push T in my stack, and this is going to correspond to the list push back. So how am I going to translate push into push back? Well, by simply calling data.pushback for that same T. So I'm going to have pop, and that's going to correspond to the list pop back. And once again, it's a simple translation. And then finally, I'm going to have top, and that's going to correspond to back on the list, which is going to say data.back. Okay, super straightforward. I'm just translating one interface to another. Now notice the list has additional interfaces that we are not utilizing. In fact, it has many, but we're only going to expose a limited number of those in the stack. I can also use the vector as the underlying data structure, and you'll notice many similarities. I'm going to have exactly the same class definition for stack, except my member variable is me of type std_vector, which means when I declare that variable std_vector of T of data rather than std_list of T. And so I'm going to have my vector by composition, just like I had list before, and all of my implementations will be exactly the same. Now, you're noticing a huge amount of similarity between the vector and the list, and of course, this is the case. And your next question, of course, is can I do this for any container that provides the same interfaces? And the answer is a resounding yes. So what we're going to do now is we're going to have the same class definition, except now we're going to have another template called container. So my data type is not going to be of type list or of type vector, but of type container. So now when I declare my member variable in C++, it's not going to be of type list or type vector, it's going to be a type container. And notice how I now have two template variables for my class. I have T and I have container. Now I'm going to have that container class by composition through stack, just like I did through list and vector. And I'm going to have the same exact required interfaces: container, destructor, assignment operator, size, empty, push back, pop back, and back. And I can have any number of additional interfaces as well. As a matter of fact, and it's important to know that any class that satisfies this interface will work as a container adapter. And the pseudocode for my push, my pop, and my top is exactly the same as it was for list and for vector. We can learn more about this in the implementation section of the stack chapter of the C++ data structures textbook.